The one today is called A Probability Perspective, and this work was just published last year, 2011. I forgot to put the reference up here, but Informal Aspects of Computing, I think, 2011. Okay, so I'll start off with perhaps the simplest sort of probability problem that I can think of. I have two children, that's true. At least one is a girl, that's true. What is the probability that the other one is also a girl? This is so simple, it's like asking what's 2 plus 2? I mean, a really simple probability problem. So everybody immediately knows, of course, that the answer is 1/3. Well, they don't actually. What they usually do is argue a lot about what the answer is. And they can't see the difference between that problem and this problem. I have two children. The older one's a girl. What's the probability that the younger one is also a girl? Obviously, it's a half. Or how about this version? I have two children. The one named Pat's a girl. Probability the other one named Chris is also a girl. Well, what I'm trying to illustrate here is that people don't have a very good understanding of probability, generally speaking. There might be hidden assumptions in answering these things. For example, do we need to assume that children are distinct? How about that they come in exactly two genders? Was that a hidden assumption? Or how about the assumption that half the population are girls? Are these assumptions needed in the solutions? And there could be other assumptions as well. So probability is not well understood. That's why casinos and insurance companies do so well. Okay. Now, the probability perspective that the title mentions is actually 4 perspectives put together. So I'll talk a little bit about what the Bayesian perspective is. The next is an information theory perspective. And there I want to basically claim that information and probability are the same thing. Finally, the formalist perspective. Well, that's where I want to get rid of all the arguments about what the probability might be and just calculate it. And finally, to provide a suitable formalism in which to do this reasoning, I will use the programmer's perspective. And to top it off, I'm going to solve the previously unsolved problem of the two envelopes. This is a problem that people have been arguing about for at least 50 years. There are still publications arguing why the probability should be one thing or another. But I don't argue, I just calculate the final probability. Now, the talk is, I think, a little bit long. And so I hope you can stay because the two envelopes part comes at the end. I might take an hour and 20 minutes for the talk. Okay. So apparently, probabilists are divided into two camps, I'm told. The older and perhaps still larger camp is the frequentists. And according to the frequentist view of probability, to say that something has a particular probability is to say that in a large number of experiments, the proportion of times that that event occurs is something. That's what they say is the probability. But what about events, what about experiments that cannot be performed a lot of times? For example, my two children. I mean, I can't really have 1,000 children and we can test out how many times we've got two girls. Or how about the probability that a nuclear war will occur or that a meteor will strike the Earth? These are not things that we can perform repeatedly. So it'd be nice if we could say something about the probability of one-time only events also. All right, so that is the Bayesian approach. Probability in the Bayesian approach is not a property of an event. It's just a measure of your ability to predict an event. And that depends, well, of course, on the event, but also on the information known to you when you make the prediction. And it will change. That probability will change as you learn more, as you learn things. And the Bayesian approach is a way of updating the probability with new information that comes along. There is a problem with the Bayesian approach, apparently, I'm told, and that is the problem of prior probabilities. That is to say, it's a way of updating, but how do you get started? To get started, you need some initial set of probabilities. How do you justify that? So I'm going to take care of that problem for you, not so much by solving it as by dissolving it, saying that there wasn't really a problem at all. And to do that, I'm going to use information theory. So, according to information theory, you have a set of messages, m sub I, and each message has a probability, p sub I. And what you talk about in information theory is the information content of a message, which is minus the base 2 logarithm of the probability. And you can take the average information content, and that's called the entropy. Okay, well, in probability, we don't talk so much about messages. We mostly talk about events. But that's not a problem. I mean, substitute event for message or any other noun that you want. It's all fine with me. So what I really want to know is the relationship between information and probability. And that abstractly is I equals minus log p. And there is a unit of information, of course. It's the bit. Now, when Claude Shannon invented information theory in 1948, probability theory was already a well-developed subject. There were textbooks, there were courses. But then nobody knew what bits and bytes were. He was introducing them. So he defined information theory in terms of probability theory, which made sense at the time, at least. But it seems to me now people know what bits and bytes are. They go to the store and they buy them. Or they send things across the internet and they talk about what rate of information flow they are paying for and things like that. We even have a physical sense that way of information now. And people don't have a strong sense of what probability is. So it seems to me that we might now do better, maybe, I don't know, to define probability in terms of information. Now, I'm not really going to advocate that or either direction of it, because whenever you've got two things that can be converted, each to the other, then they measure the same thing on a different scale. So, for example, everyone knows Celsius and Fahrenheit both measure temperature on different scales. And energy and temperature are the same thing related by Boltzmann's constant. Or energy and mass related by the speed of light. So these are measuring the same thing on different scales, and that's what I want to say also about information and probability. Okay, what is it that they measure? Well, I don't know. I don't want to invent a new word here. I think I'm just going to use the word information. Say they're measuring both measures of information. Okay. The others, they're just linear transformations, so there's really no point to them. Just maybe historical reasons why we have the two different scales. But information and probability aren't just linear transformations, so there might be a good reason for keeping both. If I have I bits and probability p related this way, and I also have j bits and probability q, same relationship between them, then I can combine these probabilities. And what happens, of course, is that you add the bits, if you combine the information, or you multiply the probabilities. It's just, and I'm I'm very, very old and I remember slide rules, and for slide rules they just convert multiplications into additions to make them easier, and that's what you could use these for as well, I guess. Okay. Now, so we got probability, C, we got information, B, and information has a unit, the bit, and if I'm going to be converting one to the other, I guess I need a unit of probability, so I'll call it chance, though I don't care what we call it really. There's also a third scale on which information can be measured, and that's state, the number of states that there are, and that is used. It's also used, by the way, for energy and temperature as well, as a third way of measuring information here. So here's the conversion chart for converting each to the other. I won't spend a lot of time on it. I think it's quickest and easiest for me to just look at an example here, some examples. And I'm going to start in the middle of this at something that has two states, like a coin. So if that's all you know about the coin, that it has two states that it can be in, head or tail, then it takes one bit of information to say which state it's in or predict which state it will be in. And that's on a different scale, 1/2 probability or 1/2 chance. Not by any kind of assumption, but by a change of scale. If there's only a single state, then it doesn't take any bits to say what state we are in or to predict what state we will be in, and it's certain that it will be in that state, and so on. Bits don't have to be integers. Here's an example. If you've got a decimal digit, that's all you know about it, then it takes about 3.322 bits to say which digit it is, and probability 1/10 for each. Also, states don't have to be integers either. So, for example, 1.5 states corresponds to 2/3 probability. Well, if you're going to buy bits at the store, you will buy an integer number of bits. You're going to have to buy 4 bits to store a decimal digit. And if you're talking about a physical system that you're looking at, maybe it has an integer number of states. I'm not sure. But just to tease you a little bit, I'm going to show you that there could be a fractional state, negative information, for example, but I don't want to dwell on that. And that corresponds, by the way, to a superdistribution in probability. Okay, so now I want to get to the main part as quickly as I can, and that's the formalization part. And all that really means is using standard scientific method for calculating probabilities. I mean, we've all done this from at least high school. So here is a high school type problem. Amanda is 164 centimeters tall, 8 more than 3 times her height at birth. Find her height at birth. How do we solve such problems? We formalize, first of all, choose a variable for each quantity that you see, and then write the given information. When you write the given information, you should not be clever. You should write that given information as closely as you can to the informal explanation that you were already given. The reason is you can't actually prove in any sense that you have formalized correctly. So you just want to keep that gap as small as possible. But once you have formalized, now you can forget about the given information, or forget about at least the informal explanations. You don't care what A and B stand for. From that point on, you just calculate. So do a typical high school calculation, find that B is equal to 52, and then the final unformalized step is just maybe to state it back in the terms that you were given originally. Now, I don't know, maybe 1,000 years ago, philosophers might have argued about how tall Amanda was at birth, and each philosopher might have had reasons why their answer is correct, but we don't do that now, we just calculate it. Well, the probabilists have not quite caught up to the present day. In my opinion, they do argue about what probabilities are, but what they should do is just calculate. Okay, so let's get to probability. A real number from 0 to 1 inclusive. 0 corresponds to impossible or false in the Boolean sense, and 1 says it's certain to happen, or true in the Boolean sense. Okay, and a distribution is just an expression that evaluates to a probability when you provide values for the variables in that expression. And when you sum all the values, for all values of the variables, you sum the value of this expression, you get 1. So that's a distribution. And for example, if n and m vary over the positive naturals, 1, 2, 3, and so on, that is a distribution. And what a distribution is telling you, well, if you provide specific values for the variables, it's telling you the probability that those are the values of the variable. And of course, if I sum it, I will get 1 for that. Okay. All right. Now, if the expression doesn't add up to 1 for all values of the variables, well, you just have to divide by whatever it does add up to make a distribution. That is, if it's properly between 0 and infinity. Just divide by those values to get a distribution. So for example, if n and m vary over the naturals, then that same expression is not a distribution because it adds to 4. Dividing by 4, you get a distribution. And now, finally, to bring programming into the picture. So a lot of these probability problems that you look at present some situation to you. Maybe they talk about something or other happening. Maybe there is a sequence of things that happen. Maybe some of the things happen conditionally upon other things happening. Maybe there's a repetition of things happening, repeatedly flip a coin, and so on. Now, the formalism that describes events happening, that's something that programmers know all about. That's just exactly what programs are for. So I'm going to use programs to describe such situations. Here are some programming notations. I am not advocating any particular programming notations in this talk. I just need some to show you how the formalization proceeds. So I'll give you these. The top one is sometimes called the empty statement or do nothing at all. The one below it, ordinary assignment, and if then else, which appears in every programming language, I think, with some syntax or other. Sequential composition, first do A, then do B, parallel, and some form of loop. So I'll stick those in. And next, what I need to do is to identify Booleans with probabilities. So I'll make the usual identification that true is 1 and false is 0, and negation, conjunction, and disjunction. I could say I'm arithmetizing the Booleans, but actually that was the original way probability was introduced. Okay, so now that now I want to generalize everywhere Booleans occur to probabilities. So for example, I can certainly generalize the condition after if or the condition after while to probabilities. That's one of the ways I'm going to generalize. And the other way I'm going to generalize is that every one of these programming notations is going to represent a distribution of final values of variables. So this is the formalization that gives it to me. OK is the do nothing or empty statement. It says all final values are equal to their initial values. So if we have a final value of x that's equal to the initial value of x, well, then this is true, x prime equals x, which is the same thing as 1 times the final value of y equals the initial value of y. 1 times 1 is 1. So in other words, if the final values are equal to the initial values, assuming x and y are my variables, they are with probability 1, according to if you execute OK. It's a one-point distribution, a one-point distribution. For any other values, final values of x and y, at least one of these two will be false or 0, so the probability is 0 that that will happen. For assignment, with assignment, well, okay, it's similar. Also a one-point distribution. Final value of x is equal to e. So if that's the case, well, then this will be a 1. And if you're executing assignment, then that will be the case with probability 1. The others, well, they turn probability distributions, combine probability distributions into one probability distribution. In a sort of fairly obvious arithmetic sense, what would have been a disjunction of conjunctions here, if I were doing ordinary Boolean style programming, becomes a sum of products for probabilistic programming, and so on. I'll show you the while loop later. So I want to get on to some sort of example here. Okay, well, there are lots of laws that we could now prove. I'm only going to mention one law, the one that I find most useful, but there are plenty of others. It's the substitution law. Same law used in the Boolean world of programming, or classical world of programming, I guess. And that is, if you have any assignment x gets e followed by any distribution at all, that's the same as that distribution, but with a substitution for x substitute e. All right, that's enough. Let me just show you a quick example. This isn't a sensible example. It's just an example to show you how these programming notations represent a distribution of final values. So it starts off by saying if 1/3, which sounds a bit funny, but what it means is with probability 1/3, x gets 0, and with the remaining probability 2/3, x gets 1. And following that, if x is equal to 0, well then, flip a coin and either add 2 or add 3. But if x isn't 0, then, well, with probability 1/4, add 4, and probability the remaining 3/4, add 5. Just a quick example to say, here's how calculation proceeds. Well, it proceeds in the usual way. Remove the definitions of the assignment and the ifs, and then I can remove the definition of semicolon. You can see the sum of products there. And finally, I can do the sum. Now, I know that's a bit quick. Don't worry about it. It's all in the paper, and you can read the paper if you want to. Let me just read the last line. The last line says, well, now the final value of x might be 2, might be. If it is 2, x prime equals 2 is true, or 1, and this is 1/6 plus 0/6 and plus the remaining zeros. So it says that the final value of x will be 2 with probability 1/6. And the final value will be 3 with probability 1/6. And the final value will be 4 with probability 0, because all of these equations will be false if the final value is 4. So it won't be. And so on, 1/6 and 1/2 for 6 here. So it gives you a distribution of the final value of the variable. Okay. Now, just by generalizing from Boolean expressions to probabilities, I've already got probabilistic choice here. I've already got conditional probability and other things with other names that I won't worry you with as well at the moment. Yeah.
How is conditional probability in here? Can you elaborate on that?
Yeah, I was worried about just as I was saying it. The answer is in the paper. Yeah. Okay, so the Bayesian theorem is an appendix to the paper. Shows exactly why probability of A given B it turns out right in this thing. So good question. Okay, now here's a nice neat little formula that says after executing S, which is really some distribution, so has a final value, a probabilistic final value. The average value of any expression E that you care to ask about is that neat little formula right there. And after executing S, the probability that some Boolean expression B is true is that neat little formula right there. And the reason those formulas are so similar is that probability is really just the average value of a Boolean expression. Okay, so looking back at that same example, if I care about the average value of variable x at the end, I just put semicolon x after it and calculate. I won't show you the calculation, but it comes to 4 2/3. If instead I care to know the probability that x is greater than 3, I just put it in the same place and calculate and find 2/3. Okay, let's do an example. Monty Hall problem, famous example. Monty Hall's a game show host. In this game show, there are 3 doors. A prize is behind one of the doors. Contestant chooses a door. Then Monty opens some door, but not the one the prize is behind, not the one the contestant has chosen either. And Monty asks the contestant, do you want to change your choice of door or stick with your original choice? So what should the contestant do? Well, my answer is the contestant should formalize and calculate. Okay, so to start with, P can be a variable that says which door Monty hid the prize behind. And since the contestant has no idea what that is, it's just a random choice of 0, 1, or 2. More formally, P prime is, well, 0, 1, or 2, each with probability 1/3, and no other value. Okay, now what door does the contestant choose? Well, I could have picked a specific door if I wanted to see. That would be fine. Perfectly good way to do it. Instead, what I said is, well, I could choose as contestant any door, 0, 1, or 2. I don't care which one. Let's say probability 1/3 for each of them. All right. Now, what does Monty do after that? Well, that depends. If the contestant happens to have chosen the door where the prize is, then there are 2 other doors, and with probability 1/2, Monty chooses one, and probability the other 1/2, Monty chooses the other. Else means the contestant chose the other door, not the one where the prize is, so Monty has only one door that he can open. Okay? Fine. So that's what Monty does. Now the contestant can stick or switch. Let's say stick. The contestant does not change their choice of door. And now what we want to know is, has the contestant won? Is C equal to P? So actually, the problem is all done here. This already expresses the answer. All I have to do is the same steps as before, remove the definitions I've given and calculate. And so the answer turns out to be 1/3. Okay? Well, right here, the contestant, instead of sticking, might have chosen to switch door, in which case the probability turns into 2/3. Okay? So the message, we don't argue about what the probability is. We don't start a blog and ask everybody's opinion. That is, in fact, what has been going on. Just formalize and calculate. And I could try to explain this, but to me, that's something like trying to explain why, let's say, 264 plus 179 should be whatever it is. I wrote it down here, 443. Yes, I could try to explain why that's that, but we're all past that now. We just add those 2 numbers. You know, we trust the formalism now. And so I would like probability to advance to that same state. So, okay.
Is the conclusion here that probability theorists don't trust a single formalism quite yet?
Well, maybe they haven't found the right formalism quite yet. I'm providing it for them here. They do, in fact, program. They do write programs, some of the books, not all of them. that describe the situations, but they only use those programs for simulation purposes to gather statistics and then decide what the probability is. They don't use them as a formula that already expresses the answer and from which they can calculate. Okay, so here's the problem I started this talk with. I have 2 children. What should I do with that? Well, formalize. Let's C and D be the genders of my 2 children. Okay, girl or boy, each of them. I'll just pick a value for each of those for calculation purposes. Let's say girl is 1 and boy is 0. Now it says at least one is a girl, C prime or D prime. At least one of those 2 has value true or value 1. Now, Boolean expressions in general are not distributions, so in case it's not, I'll normalize it. In fact, it's not, but now it is. And then the question was, what's the probability that the other one is also a girl? Well, that's just C and D. They are both girls. So there's the calculation. I won't spend time again, but I just wanted to show it to say how long it is. And you can see over on the right what the steps are. So it's not long and it's not hard. And you get the answer 1/3. In the next version, I have 2 children. The older one's a girl. What's the probability that the younger one is a girl? All right, let C be the older one. Let D be the younger one. Then the given information is the older one is a girl, right there. And I'm asking, is the younger one a girl? Calculate, I get a half. Okay. Now, I was asking some questions about what our assumptions are. Do we assume that the children are distinct? Well, it's the formalism that answers that. I chose a variable for each child. So yes, that means they are distinct. Now, if there had been raindrops in a barrel, I suppose that you cannot point in the barrel at a particular raindrop. You can't say that raindrop right there. I mean, raindrops lose their identity when they fall into a barrel. But maybe what we can say about raindrops is how many of them there are in the barrel. Why? Well, maybe I know the volume of a raindrop and the volume of the water in the barrel, or the weight or something. So let n vary over 0, 1, and 2 raindrops. And I'm asking how many of them are acidic. So, oh, sorry, this is the number of acidic raindrops. I am given that at least one of them is acidic and asked the probability that they are both acidic. So I've phrased the question, after which I calculate the answer, 1/2. Another question was whether the children come in exactly 2 genders. Well, yes, I clearly gave those variables 2 values. Made them Boolean valued. But it's possible, of course, that there's any number of subgenders of girl and any number of subgenders of boy. That is not excluded, but there are those 2 genders at least. Did I assume half the population of children are girls? Well, you might be a little surprised at this particular answer. The answer is no. Why? Well, according to the information theory perspective that I've given you, probably 1/2 for girl and 1/2 for boy doesn't mean anything about the general population. It just means that we have no idea whether a particular child is a girl or a boy. That's what probability 1/2 means. In fact, according to the problem, I don't even know if there are any other children in the world. Maybe my 2 children are the only children in the world, according to the given information in the problem. Okay, but if it happens there are other children in the world, and we know something about the distribution of boys and girls in that general population, that can change our answer. So let me suppose that 1/3 of the general population are girls, just to see what happens. Well, formally, if 1/3, then this child has value girl, otherwise value boy. And similarly for my other child, with probability 1/3 girl and probability 2/3 boy. And then I'm given in parallel with that information about the population of the children of the world, I'm also given that at least one of my children is a girl. And then I'm asked, are they both girls? And I calculate. And I get the answer 1/5. Slightly longer, but as you see from the right column, no more difficult.
Aren't you also assuming that the children are not identical twins? That would make the gender not determined.
Possibly. I have to think about that. But if my only further given information, what I've done is to formalize the further information that 1/3 of the general population are girls, not knowing anything about identical twins. But if you want to add some further information about identical twins, I might well modify what I've got and come to a different probability.
If all children were identical twins.
All right.
So you're making assumptions about
Yeah.
proportion.
Right. The more I know, I can write down more information there. It's going to change my probability. Quite right. That is exactly the Bayesian approach. Okay. So I'm looking at this calculation, but it seems to me that actually it can be automated, this calculation. There's nothing difficult enough in it to prevent automation. So you buy yourself a probability calculator, you express the problem, you push the button, and it tells you the probability, just like our regular arithmetic calculators. All right, this is the first example that involves a loop. So I have a 2-position switch, flipped some number of times. At each time, including initially, before the first flip, there is a probability 1/2 of continuing to flip and probability 1/2 of stopping. What's the probability that the switch ends in its initial state? Okay, it's a loop. I'm flipping a coin repeatedly, and while it shows a head, do flip switch. Okay, it's not fully formalized yet, but at least I'm just showing that it's a loop at the moment. Okay? Now, when you have a loop, it's a little bit different than what I've been showing so far. When you have a loop, you actually need a hypothesis distribution for the loop. And as soon as you come up with such a hypothesis, and I don't claim that that's easy, as soon as you come up with such a hypothesis, you can then get rid of the loop. You can replace the equation with the loop in it by an equation with if then else and semicolon and okay, and we know how to deal with all of those. Now, I'm not going to take you, so further formalization is while coin shows head, okay, that's probability 1/2. Then flip the switch. Well, Boolean variable B gets not B is a perfectly good formalization of flipping a switch. And finally, I need to formalize the hypothesis. And I don't claim it's easy, but I'm just going to show you what my hypothesis is. This is the one that ends up working. So to say that the switch ends with the same value that it began with, B prime equals B, that's okay. So okay is true if the switch ends where it started. If okay is true, or 1, that's 2/3. So it's saying the probability is 2/3 the switch ends as it started. If it ends differently from where it started, okay is 0, so that's 1/3 probability. And here's the proof, which again I won't go through. I'm just proving that the right-hand side is equivalent to the left-hand side. I started with the right-hand side because it had more interesting calculational possibilities. For that reason, something I learned from Dijkstra. Anyway, that's a proof that that hypothesis works. Now, you might not guess the right hypothesis to start with. I usually don't. And then the proof attempt fails. But when the proof attempt fails, the way it fails usually gives you some pretty good information about how to fix the hypothesis. And as a matter of fact, we have a piece of this department, and Marcia Chechik has worked on this for quite a while, on how to, not for probabilities, but on Boolean programming, how failure of a proof can help you to come up with a better hypothesis. So I have some hope that while this isn't fully automatable, perhaps, a lot of it is as well. Okay, so I'm finished with that flipping switch. Now I'm going to show you something amazing, at least it amazes me. So, start off with p gets 1, some variable p gets 1. Going to flip a coin, and as long as it's showing a head, I'm going to double p. So the first time I see a tail, I stop. Okay? Now, okay. So my question's going to be, how many times am I doubling p? So I'm going to introduce a variable to count how many times I double p. I'll set it 0 to start with, and I'll increase it by 1 every time I double p. T stands for time. I'm measuring time either by doublings or by iterations, either way.
No, T stands for toss.
All right, T stands for toss then. How many times we toss. Okay. 120. So here's, I'm going to save a little time and just show you the distribution. I usually forget stuff like this to begin with, but the proof tells me proof effort tells me that it's necessary. And it just says that in the end, well, if it's time, time doesn't go backwards. If it's toss, toss is some natural number, not some negative number, and so on. The next part says that the final value of variable p is going to be some power of 2, and it's the final value of t that's going to tell us which power of 2. And the last part says, well, if p ends at 1, then the probability is going to be 1/2. If p ends at 2, then the probability is going to be 1/4 that it ends at 2. And the probability that it ends at 3 is going to be 1/8, and so on. That's what that's saying. Okay, skipping this proof to save time. What I'm really interested in here is the average value of variables. So first, the average value of t, final value of t. Well, I just write down the distribution and follow it with a t and calculate. And what do I get? 1, saying that on average, p will be doubled once. Okay, that's not very amazing at all. But the loop body is executed once. Here's the amazing part. The average final value of variable p is, all right, write the distribution and follow it with p and calculate, and you get infinity. And the reason that amazes me is that on average, we double p once, and on average, its final value is infinite. To me, I thought at first there must be something very wrong, but it's not wrong, it's right. That is the average final value of p. I'm amazed. I don't know if you are. Okay. So now to the promised 2 envelopes. Okay. So imagine that I have 2 envelopes here. No. You're wrong. It defies my intuition.
Double the value, but double value is half the probability.
Yeah. It's just taking a sum. The sum is a half. Here's why. A half. Yeah, it's a divergent sequence. So it's 1 with probability a half, and it's 2 with probability a quarter, and 3 with probability an eighth, and so on. So it's 1 plus 1 plus 1 plus 1, and on. Again, that's not an intuition, that's the calculation. All right. It's what the formula said. It's the sum in the formula. Okay, so 2 envelopes. So I have 2 envelopes right here, and there's some money in each envelope, and you can choose whichever one you like, and having chosen it, you can look in the envelope if you like. I don't mind. And then you can either stick with what you've got or switch envelopes if you'd prefer. Okay? That's the basic problem. Well, I'm going to start with a simple version of it in which I'm telling you that each envelope contains from $1 to $100. Okay? Now, in this version, there is a best strategy, and it's not that difficult to see. So you look in the envelope, and if what you see is too small, less than half 100, switch. You got a better chance of increasing than if you stay. Okay, and if you see more than half 100, well, stick with what you've got. So that's easy. What if it's 10 to the 100th instead of 100? Well, okay, same problem, right? If you see less than half of that big number, switch, else stick. Well, now I'm just going to remove that upper bound altogether. Okay, so the upper bound is infinity, if you like. Well, you can look in the envelope, and whatever you see, it's going to be less than half infinity. Therefore, I guess, you should switch. Whatever you see, you should switch, right? That's what it seems. In fact, the great mathematician Blaise Pascal thought that was the right answer, but he was wrong. Okay, let's change the problem a little bit. Each envelope contains a positive rational amount. This particular version, a positive rational amount. One contains twice as much as the other. Choose one, stick or switch. This one has been the subject of debate in academic journals for at least 50 years, and the debate seems to rage onward. Okay, one of the arguments goes like this. Let the amount in whichever envelope you've chosen be x. Should you switch? Well, you stand a chance, if you switch, of gaining x, doubling, with probability of half. But you stand a chance of losing half of what you've got, with probability of half. Well, that's x by 4, which is at least positive. As long as it's positive, seems you should switch. Oops, I went one too far. Seems you should switch, right? That's what it's saying. And if you know you're going to switch, there's no point in even looking in the envelope. You know you're going to switch, so you can play the same game again. I mean, same reasoning says switch again, and again, and again.
So when you say there are two envelopes,
Yeah.
is there one called 1, the other one has written on it 2? I mean, since you're not going to look at the first envelope,
Okay.
might as well fall.
Yes, you're right. You're absolutely right. So James Israel is pointing out that actually there's more than one way to formalize this. And they will all come out with the same answer. The way I've chosen to do it is,
They don't come out with the same
oh yeah, because it's like the children, right, if they're identified. But
No,
the point is you don't know the amount in the envelope you choose. I can put a 1 and a 2 on the envelopes. I can call the one you choose 1. But you don't know the amount in it.
Your argument that since I don't have to look at the first envelope,
Yeah.
in your argument, you will take the first envelope, don't look at it, pick the other one. Now, she says, why did you even bother? Call the second one the
Right.
first envelope. Just take it.
Right,
So you don't switch.
right. I agree with what you just said.
So her strategy will give the correct answer.
No, this isn't correct.
Well, I mean,
This
that's
strategy is not correct. Look, here's another argument that says let the amount in the other envelope, the one you didn't choose, be y. All right, if I'm going to switch, I might already have the bigger amount, and I'm going to lose y by switching. But I might have the smaller amount, and so I'm going to gain y by 2. This is negative, and it says, this kind of reasoning says stick. This is the kind of debate that happens. This reasoning, none of this reasoning is right. None of it's right. Okay. So, here's yet another version of the problem. Well, I'm going to tell you how I choose the two values, x and y, but you're not allowed to watch me do it. What I'm going to do is start x off at 1, flip a coin. As long as it's a head, I'm going to keep doubling x. Okay? And when I see a tail, I stop doubling x. And once I've got x, then I take y to be twice that. But I do all this, you know, where you can't see me do it. And then I turn around and I say, that's how I did it, but you didn't see me do it. Choose an envelope, look if you like, stick or switch. Well, an argument says that was irrelevant. So you flip the coin. When you're finished, all we know is there's some amount in one envelope and in the other one twice as much. All we know is there's two amounts, one's twice as much as the other, same as we knew before. That's one argument. Also wrong. I mean, all these arguments are wrong. Okay. So what we should be doing is stop arguing and start calculating. And so that's what I'm going to do. Let the amount in one envelope be x, the amount in the other envelope be y. All right. Hello. Welcome. So this is how we pick the amount in an envelope. With probability of half, z gets x, else z gets y. All that's saying is when I pick an envelope, I don't know which one I've got. I don't know. So z's what I've got. I don't know whether it's x or y. Okay, I could stick or I could switch. That's sticking. And then I might wonder, what's the average value of what I've chosen? And I can calculate it. And it's not a surprising answer. It's x plus y over 2. Okay, on average. You don't know what x and y are, but halfway between is what you can expect on average. All right, if I want to do a little bit better, I will have, this is the next one version then is instead of sticking, I decide to switch, but it doesn't change anything. It's still the average of x and y. And now if I want to do better than that, I keep talking ahead. Here, instead of knowing what the average value I end up with, I might want to just ask, is w greater than z when I finish? That is to say, have I gained anything by switching right here? And the answer comes back, x not equal to y over 2. In other words, if the values x and y are unequal, the probability that you have gained by switching is a half. And the probability that you lost is also a half. Okay, instead of asking the probability that I've gained, I might want to say, how much have I gained? So that's w minus z, my final value after I've switched here, minus the initial value, or the value before I switched, which would be not switching. So this is my profit I get by switching, and I get the answer 0, profit by switching. Okay, let's go to the version now where we put some strategy into it. Some strategy says you're going to look in the envelope, and if what you see is too small, smaller than some strategic amount s, then you're going to switch. And otherwise, you're going to stick with what you've got. All right, what's the profit? That is to say, what's the switching amount minus the sticking amount? Okay, the answer here is a little bit complicated. And in order to simplify that a little bit, it will help if I tell you something about how these numbers are chosen. So in the first version, x was between 1 and 100, and y was between 1 and 100. And with those choices, the answer looks like this. It's a parabola facing downward, and it has a maximum. And I can solve to see what the maximum is, and I find its maximum value is 50. Not a surprise. And it occurs, and so if I put 50 in for the value of s, then I find that the switching profit is 12.5. And that is the best you can do with this way of choosing x and y. So just compare it to 50. Let's try the next version, where the only thing we know about the two values is that one is twice the other. We know nothing else about how they are chosen. Well, in that case, it tells me that the switching profit minus the sticking, the value I get by switching minus the value I get by sticking is on average 0. So if that's all I know, that's the answer. So the real answer to the question about the envelopes, as I was asking, is it doesn't matter whether you stick or switch in the famous version of the problem. Let's put some strategy in and say, if Z is less than some strategic amount, so I'm going to look in the envelopes and I'm going to have some amount in mind. And I'm going to say, if I have less than that, I'm going to switch. And otherwise, I'm going to stick. How does that work out for me? Well, okay, this is the formula. Unfortunately, there's still an x in the answer for the formula, so it kind of depends on what x was, which I don't know. But to get rid of x from the formula, I can put in some information about how x is chosen. So if I use this scheme of starting at 1 and doubling for a while, and then choosing x to be twice that for the y envelope, okay, here we pick an envelope. Now we look in it, compare it to this strategic amount s, which is still to be determined, decide whether we stick or switch, and see what our profit is. And it's a very interesting expression. It says, if for s you choose the value 0, which is to say, this is going to be false, and I'm always going to stick, then this is 0 over who cares. In other words, the profit is 0 if I always stick with the envelope I had. Actually, we already calculated this before. If you choose s to be infinite, which is to say I always switch. Whatever I see in the envelope, it's less than that, I'm going to switch. Again, it's 0. But if you choose any finite amount and it doesn't matter which amount, the answer is 25 cents. Your profit, by having a strategy to switch if you've got too small an amount, on average, you gain 25 cents, no matter what that S is. I think that's kind of amazing. Well, here's another example I tried just to see what's going on. Instead of doubling, I'm going to triple. All right? While I just keep flipping a coin, and I keep tripling x. And when I stop tripling, because I've just seen a tail, then I take y to be triple what x is. And now, pick an envelope. The strategy of z is less than some strategic amount. Now, I've told you how I'm choosing x and y, though you didn't watch me do it. So you do know at least that it's a power of 3. So I'm going to make my formula a little nicer by comparing z to 3 to the n. And I get this very interesting expression, which says, as before, if your strategic amount is 0, well, actually, this is the value of n. So if it's less than or equal to 1, n being 0 is the amount being 1. So in other words, if you choose 0 for the amount that you compare to, then that's always stick and you get nothing. On average, you gain nothing. Or if I choose infinity, then again, that's always switch and you get nothing. But if I choose some amount in between, the interesting thing is that this does matter what strategic value you choose. The larger the value you choose, the larger your average profit. But you have to choose a finite amount. You can't just say, I'll choose infinity. It's the possibility that the amount will be more than that that gives you this answer. So I think that, too, is rather interesting. So it was an open problem. I've solved the open problem, but I've gone on to propose new versions of that open problem to say it's all the same sort of calculation. So the last two were both my own versions of the problem. Yeah.
Suppose I decide with my n according to algorithm. I open the first envelope and say, well, my n is such that it's much larger than this number that I'm seeing. I could have decided on n beforehand. I could decide on n afterwards.
Right. Now, so I've considered even more versions of this in the paper. And one of the versions I considered is where n is, or s is chosen again differently for each time you run this. Well, one version is you choose it randomly. And again, you profit by that. So there are different ways of choosing the value, and for each one, I'm willing to do a calculation and see what the answer is. I've done more of them in the paper than I have time to talk about here. And in fact, I'm going to now skip a bit. I like to say jump to conclusions, so I'm going to skip all of this stuff and come up to the conclusions here. Okay, so in this talk I talked a little bit about the Bayesian perspective, the main point being that probability is affected by what you know, and it's updated as you learn new things. Okay? Then the problem of prior probabilities disappears. The reason you get those probabilities initially, the uniform distribution initially, is not by some unjustifiable assumption. It's by a change of scale. All you know initially is the number of states, perhaps. And all you're saying when you say uniform probability over those states is all I know is the state space. I don't know anything more about it. Okay. The next I talked about the information perspective, and I tried to argue that probability and information are the same thing, a change of scale. And the main part was on the formal perspective, formalize, calculate, and unformalize. And I suggested that probability problems are very usually described as some sequence of events, or even parallel events, I don't mind, or some repetition of events, and so on. So programs. So using the formal methods view of the world, programs are not just something that controls a computer. Programs are also mathematical expressions in their own right, and now I'm showing how they can be interpreted as probability distributions. So that tells us how to formalize, how to calculate, and I have some hope that a good deal of automation can take place so we can end up with a probability calculator. Yes?
Regarding the Bayesian steps, what about when the Bayesians make more complicated something? Let's say theta as a prior, let's say gamma.
Right. So what they're doing is one step into what I would do. I would start by saying, here's the state space. That's a uniform distribution. Oh, we know something more about that state space? Do we know something more? Fine, I'll update it to that. And they're taking that next step as being their initial. I could say, oh, I know this, that, and the other thing many steps in, and they could start there if they want to. Okay? So that's my talk. There's more in the paper. Thank you very much. I hope to see all of you tomorrow. Questions? More questions?
So how do continuous probability distribution?
Right. So I didn't talk at all in this talk about continuous probabilities, nor do I in the paper. They're entirely discrete. I suppose in continuous probabilities, what I've represented as the sums become integrals and so on. I'm hopeful that there's some way to do all that, but I haven't done it. Anya, do you know a bit more than that about that? No, don't want to add anything. Okay. Yes, John.
It seemed to me that the reason why you started with 1 and started doubling each time and probably 1/2 was that seemed to be a useful way to do two amounts in two envelopes, of which one is twice the other, right? But of course, your result depended very much on how you did that. Perhaps what you put your finger on here is that our intuitions about how you might create two amounts, one twice the other, have underlying facts about them that we're missing. And perhaps if you picked some other way of coming up with a program that would result in two envelopes, one with twice the amount of the other, you've gotten some other result. Would you say that's correct? I'm just trying to
Yes.
see if I understood what you said.
Yes. I mean, all I know is that however somebody suggests we come up with the values for x and y, I want to be able to formalize that as a program and do the calculation. And yes, of course, it might, if you choose any other way or put any further information into it, we may come up with a different answer. What I maybe should add about this amazing average part is that, so we're all familiar with the fact that an average doesn't have to be any one of the occurring values. For example, perhaps, you know, there are the average couple has 2.3 children. Doesn't mean that any particular couple has 2.3 children. The news is that average not only doesn't have to be any one of the given amounts, it doesn't have to be within the bounds of the smallest and the largest of them. So it could even be outside those bounds. That's what seems strange to me. Yes?
So with regards to the two envelope problem, it just seems that this is just sort of a formalization of the subjective Bayesian sort of view on the problem. Because, I mean, what you've really said is that our strategy changes as our information increases, right?
I'm not quite sure if our strategy changes as our information increases, but I mean, you can formalize the strategy and formalize the information.
You can formalize, if you can formalize the information. I mean,
Yes.
you've provided solutions to the problems provided you have information about how
Yes,
envelopes of
that's
things are
right.
distributed. But I mean, that seems just to be the subjective Bayesian approach anyway, right? I mean,
Yes.
by assuming that you're given more information, of course you can conclude.
Actually, I tell you my problem in answering your question. So I'm claiming that probability is a measure of your ability to predict what's going to happen next. As you gain information, it may be true that you lose ability to predict what's going to happen next. In other words, if I'm talking about two possible outcomes, probability of half means I have no idea what's going to happen next. So that might be the result of learning. I might have thought the probability was a third from what I knew, but now I've just learned something more. The coin is biased in some way. Now I've just learned something more about it. I calculate. I find out I'm less able to predict the next event than I was when all I knew was that there was a particular bias or something. I hope I've made that clear.
I understand what you're saying.
Yeah. Yeah. Yes. Yes. Well, all I'm saying is that they do sometimes use programs, but the way they use the programs is to run a simulation of the events and collect statistics on the outcome. In other words, what they don't do is to use the program as an expression that already tells you the final answer, if you just know how to simplify it, how to calculate. Now, I'm perfectly happy to run programs and gather statistics too, but that wouldn't be new.
But it would be more sort of efficient and accurate, to always, any program you've designed to run a simulation that you're going to collect statistics on, you should instead do this kind of calculation on a version of that same simulation program.
Well, here's an example where I think I might write the program, and I'm going to need some hypothesis for any loop that's in there, and none comes to mind. What am I going to do? Well, how about run the thing, gather some statistics, and use them to formulate a hypothesis which you can then prove. So that might be a good reason to run the program. If I've understood your question correctly, you're asking about the relative value of execution versus calculation from the program. And I'm trying to say sometimes maybe execution is the best way to proceed. So I'm certainly not trying to take anything away from doing that. I'm only trying to add this alternative for calculation. Yeah, you could. So execution, and even if I've proven it, I might still want to run it for a demonstration purpose, or maybe like call it testing if you like.
No, I think that's a very interesting suggestion because at times people often run Monte Carlo simulations knowing exactly what distribution they're trying to calculate, but it's just sort of easier to write a program that simulates the situation in each model.
Right.
And then just, say, okay, here's an empirical distribution. But it seems like using this kind of system, you can always just calculate that distribution. If you know what it is you want to calculate right from the program, you don't have to run it a number of times.
That's right. In principle, you can always calculate, but in practice, sometimes it might turn out to be difficult. Running it, the program, is always easy. Hugh.
So could you take, say, a Monte Carlo simulation and partially evaluate it statically with your techniques and maybe speed it up potentially?
Right, and I think that was also what Lev was saying. You could combine the two.
But is
Yes,
that
you can
different?
do some calculation, some execution. I don't see why not. Sure. Yes. Anything else? Well, thank you very much. See you tomorrow.